everybody. Let's start with the last result that I finished in the last lecture. We discussed this result that the derivative of an analytic function in a domain is itself an analytic function. We started from Cauchy integral formula by this kind of formula that f of alpha is equal to 1 by twice pi I integral over the boundary C of f of z divided by z minus alpha. And finally we proved these results, this kind of result of the expressions of f double dash alpha, and from that expression we proved that this kind of integral f z divided by z minus alpha dz, this kind of integral can be written in the form twice pi I into f dash alpha. Similarly, we can prove the higher order results. In general speaking, the nth derivative has this kind of expression, that factorial of n divided by twice pi I integral of f of z divided by z minus alpha to the power of n plus 1 dz. And from that result, we have proved this results, that integral of this kind of expression can be written as twice pi I divided by factorial of n into nth derivative of f at the point alpha. So let's start with the application of this result and few more results. And finally, my target is to prove the Leopolis theorem in this class. And if possible, I will also finish the fundamental theorem of algebra. Okay. So over here, let's discuss an example. Suppose C is a curve like this kind of curve. Suppose I discussed this kind of curve earlier, a square with the sides of which are parallel to x-axis and y-axis, this kind of square. This kind over here, this is line, then this one, and finally this kind of line. And the coordinate axis, see, this is the x-axis and this is the y-axis. So this is our x-axis and this is our y in this negative direction. This is negative y-axis and this is negative x-axis. Now this is a square in which the straight lines are x is equal to plus minus 2 and y is equal to plus minus 2. That means this is the straight line x is equal to 2. This is the line x is equal to minus 2. This is y is equal to 2. And over here, this is the line y is equal to minus 2. So let's consider this boundary. This boundary of this square as the curve C. Now over here, what we need to do, we need to evaluate the integral, this kind of integral over this curve C for the function tan of z by 2, z by 2 divided by z minus x0 whole square dz. Let me just make it a bit larger. So this is the integral, and it is given that minus 2 less than x0 less than 2. So x0 is actually a real number, because only in case of real number the this kind of inequality is true. In case of complex number, these inequalities do not hold. And so we can consider that x0 is a real number and it lies in between minus 2 and plus 2. So in this picture, what we can say that the position of x0 lies on this real x-axis. this might be the position of x0. Because of the fact that minus 2 less than x0 less than 2, we can say that x0 lies in this kind of open interval on the real axis. So what we mean over here, that x0 is a point that lies inside this curve C. Therefore, if we need to find out the integral over C, tan of z by 2, divided by z minus x0, z minus x0 whole square. In that case, which function should we consider as f of z? And actually our target is to apply this kind of formula over here. This is, you see, f of z divided by z minus alpha square dz, whole square dz is there. So over here we need to identify this f of z, and we need to apply this kind of formula. So clearly this function, this expression in the numerator, that can be considered as equal to f of z is equal to this tan of z by 2. And you see this is undefined when this z by 2 would be is equal to some even odd multiple of pi by 2. Let us consider, for example, plus minus pi by 2. Or you can say that when z is equal to plus or minus pi, this function becomes undefined. Now, what is the numerical value of pi? Numerical value of pi is equal to 3.14 approximately. So, hopefully, in this point, tan of z by 2, if you consider f of z is equal to tan of z by 2, then this kind of point, maybe if this is 2 unit, this may be 3 unit, and this might be the position of plus pi, and over here this might be the position of minus pi. So these 2 points, plus pi and minus pi, these 2 points, z is equal to plus minus pi, these 2 points, they lie outside this contour C, outside this closed region C. So we can say that within and on this curve C, this function f of z is defined, and we can now further differentiate this function. We shall get f dash is equal to half of 6 square z by 2. What I mean to say is that this expression, if the z is defined within and on this curve C, so we can conclude that the function f is analytic within and on the curve C. That was the main point, that if you consider f of z is equal to tan of z by 2, in that case we can say that the function f of z is analytic within and on this curve C. And if it is so, in that case we can apply this formula of derivative, and we can now say that this becomes is equal to integral over C is f of z divided by z minus alpha. Over here alpha is equal to this x0, z minus alpha whole square. So over here we are taking alpha is equal to this x0 dz, and that expression would be is equal to twice pi I multiplied by f dash at the point alpha. Alpha means this point x. So applying this kind of formula, we can now evaluate the value of this integral. Therefore, if we take f of z is equal to this numerator tan of z by 2, then we shall have, then f dash z, this expression would be is equal to half of 6 square z by 2. So what we can say by this kind of formula. So you see This kind of integral can be written as like this, z minus, you can write z x 0 over here, no problem is there. In that case you have to write x 0 over here as well. And then its value would be is equal to twice pi I into this 6 square. In place of z, just put x0. Okay, can write in this fashion x0. So that is the final result or the value of this integral. So you see that this kind of integral becomes much more easier to integrate, because these are all complex valued expressions, and by the help of this kind of formula, these are much more easier to compute. So what is the final expression? Just 2 and 2 will be cancelled, so we shall have simply pi I into 6 square x0 by 2, pi I into 6 square x0 by 2. This is the final value of the expression. Okay, so you can consider this kind of example. Now I am leaving a homework for you. One example. Okay, so if you consider the same curve, um, the same kind of curve, just in place of this tan of z by 2, I'm just considering cos hyperbolic of z. And over here, let's consider this one a bit simple, z to the power of 4. So you can apply this kind of formula with n is equal to 3, and you will get the final relation, final value of this kind of expressions. So these are few easy examples as an application of this formula. Hmm. Now I am going to discuss an inequality that is known as Cauchy inequality. I am writing this one as a theorem. Hmm. Cauchy inequality. Cauchy inequality. Hmm. What does it say? It says that it is actually we can we can consider this kind of expression. Hmm. Okay, let me just copy this one, and from this result we shall prove this Cauchy inequality. What does it say? It says that if f is analytic, hmm, analytic within and on this kind of curve C, and what is this C? C is equal to the circle Z, so that Z minus alpha is equal to this kind of circle with radius r, small r, okay, sorry, capital R. And what is m? M is a number which is maximum of f of z, maximum of modulus f of z. Okay, maximum of modulus of f of z, where z belongs to, so where this z belongs to this curve, C. That means z is a point on the curve C. If it happens, in that case, what we can write? Then we can write that modulus of this expression, modulus of this nth derivative taken at any point alpha, this quantity is less than or is equal to n factorial multiplied by capital N divided by r to the power of n, or n is equal to 0, 1, 2, etc. So this is the statement of Cauchy inequality. Now, in order to prove this result, we can consider this result, the nth derivative, the expression of nth derivative, Hmm. Let's prove this result. We have what we have. We have this kind of result. Now, from this result, if we take the modulus on both sides, hmm, from both sides, then what we shall have? Let me write this result like this. So, if we take the modulus, hmm, then modulus of this expression multiplied by modulus of this expression. Hmm. Now you see modulus of twice pi I, that is actually twice pi, and on the numerator modulus of a real number, that is the real number itself. So we shall have modulus of this expression is factorial of n divided by twice pi. Hmm. And you see this kind of expression in integral, modulus of an integral is less than is equal to integral of the modulus. That means we can take this modulus sign inside this integral. This expression can be written as modulus of dz. This expression becomes modulus of f of z divided by, over here we can write this modulus of z minus alpha to the power of n minus 1. And remember, this is an integral over this curve C. That means the points z, these points z, they all lie on this curve C. Now on this curve we have this maximum value. On this curve, capital M is the maximum value of the modulus of f of z. So we can say that this quantity, you see these quantities on this curve, f of modulus of f of z, this kind of expression, that should be less than or is equal to capital M, where when z is a point on the curve. So on the curve C, f of z is less than or is equal to m. Okay. So we can now say that this quantity is further, this total expression is further less than or is equal to, you see over here in place of f of z we are putting capital M. And on this curve C, if you look at the equation of this curve C, on this curve C we have z minus alpha is equal to r. Z minus alpha is equal to r. Modulus of z minus alpha is equal to r. So in place of this modulus of z minus alpha, we can put capital R. All right. And what would be the value of this expression? You see, over here this constant can be taken outside the integral sign. So this is integral of modulus of fz, and this is nothing but is equal to length of the total curve. Integral of modulus of fz is equal to the length of the total curve. So over here the curve C is actually a circle with radius r. Therefore its length, or the perimeter length of that circle, is equal to twice pi r. So over here, in this expression, we can put twice pi r. So just put twice pi r, and now let's make it simple. We get the final result. This expression, you see, this twice pi and this twice pi will get cancelled. So we have simply factorial of n, and this r and 1 r will get cancelled. So on the right hand side we have factorial of n into m divided by r to the power of n. That was the final result or inequality we wanted to prove. So modulus of, modulus of this inner derivative at the point alpha is always less than is equal to factorial of n into m divided by r to the power of n. So this was the proof of this Cauchy inequality. Similar kind of result can also be proved whenever we consider different kind of curves. Just the length of the curve is to be used over here. The length of the curve will be changed. So accordingly, the result or the final expression will have certain changes. Anyway, well, I'm not going to discuss all these detailed results, but in case of this kind of circle, we shall in future use this result directly because this is a standard result known as Cauchy inequality. So next, I'm going to discuss a definition. The definition of integral function or entire function. Integral function or entire function. What is this? The definition of integral function or entire function. It says that if a function, if a complex valued function, of course, if a function, let me write f of z, if this function f of z is analytic in finite complex plane, is analytic in finite complex plane. Now, what is finite complex plane? I shall discuss all this. If the function f is analytic in finite complex plane, then it is called integral function or entire function. Okay. Now, what is finite complex plane? Let me draw this over here. Remove this one first. Now, finite complex plane, it means that if we have not this kind of, say, if we have this kind of complex plane, suppose this is x-axis, this is y-axis. Now consider the part of this complex plane, because this, you see over here, x and y, these are infinitely extended. In general, x should vary from minus infinity to infinity. Similarly, y should also vary from minus infinity to infinity. But if you consider the portion of the complex plane which can be written as the inner portion of a circle, inner portion of a circle of finite radius. Say if you consider a circle, this kind of circle, there this is suppose the radius say small r of this circle. Now if we consider that r is any arbitrary real number, but r is finite, this is less than infinity, r is not equal to then we can say that r this interior region, we can say that this interior region lies within a circle of finite radius. That is the idea. This interior region is called the finite complex plane. So what is finite complex plane? We can say that if you consider this kind of set z such that modulus of z, this modulus is less than some finite number r, or you can say smaller, less than some finite number small r. You see over here, if you consider any point z, then this is the modulus of z. Okay, so this is the set when this is the set of all such z such that this modulus of z is less than r for any finite r. Okay, for any finite r, finite real number r is of course greater than 0, then this set, let us call it capital A, then this set is called the finite complex plane. And outside this kind of region, will be called the infinite complex plane when r is arbitrarily large. R is any real number. So we can take r larger than any large number. So that zone, that is called the infinity. So infinity, in case of complex number, infinity does not just imply only a single point. It is actually a collection of many points. It is the entire region. This region outside the circle, this region is known as the infinite complex field, or simply speaking, the infinity in terms of the complex numbers. Clear? So this is the idea. This is the zone. This interior part. This interior part. This is the finite complex plane. This shaded region. This is the finite complex plane, and outside this region, that is known as infinite complex plane. This kind of regions. Where R is of course any real finite number. All right. So if a function f of z, if this kind of function, if you consider a function which is defined within this finite complex plane, and it is analytic within this kind of finite complex plane, then such function f of z is known as entire function or integral function. Okay, this kind of integral function or the entire function. So this is the definition of entire function or integral function. Now let's move to the statement of Leopolis theorem. The statement of Leopolis theorem is all about this kind of entire function or integral function. So we have a theorem, Liouville theorem. L-I-O-U, L-I-O-U, V-I-L-L-E, Leopolis theorem. Be very careful about this spelling. What does it say? The statement is very simple. It says that a bounded integral function is constant. A bounded integral function is always constant. All right. This theorem says that if we have an integral function, the integral function means an analytic function which is analytic in the finite complex plane. A function which is analytic in a finite complex plane. Now, if that function is a bounded function, then that function must be a constant one. That means, other than constants, if you consider any other such integral function, then such other integral functions would never be bounded. That means, other than constant, a variable integral function, if you consider a variable integral function, then such variable integral function will never be bounded. That all such variable integral functions should be unbounded quantities. Anyway, let's prove this result. So over here, consider any arbitrary point alpha. You can also consider. Let me just remove this picture. Instead of considering this kind of sorry, instead of considering this kind of complex plane, now you can also consider any point, say alpha. In this finite complex plane. Of course, finite complex plane means we have to draw a large a circle in center at the origin. However, over here we are not drawing a circle, rather we are drawing a circle around this point alpha, because you see you can easily shift the origin at the point alpha. So it is a matter of shifting the origin. So in case of shifting all such origin, forget it. Just we are considering a circle around the point alpha. Maybe a circle of any arbitrary radius. So over here, this is not a good circle. This is a or this looks like a circle. So we consider a circle with radius small r. Okay. Now, as because the function is analytic in this entire complex plane, in this finite complex plane, then of course it must be analytic within and on this kind of curve. Let us call it this curve. Let us call this curve C. Okay. Now you see over here by Cauchy integral formula we can have this type of result. F of alpha is equal to 1 by twice pi I integral over C f of z divided by z minus alpha dz. And we already also got this result, the expression of f dash alpha. We got the expression of f dash alpha. What was the expression of f dash alpha? 1 by twice pi I. 1 by twice pi I integral C f of z divided by z minus alpha whole square dz. This is the expression we have. Let me write this expression over here because I already have these expressions. So let me just copy and paste them. So this is the expression of f dash alpha. So we have this expression of f dash alpha. And over here, if we now take the modulus on both sides, then we have this type of result, modulus of this expression multiplied by modulus of this expression, and modulus of twice pi I is nothing but is equal to twice pi, so forget about it. And then again this expression can be written as less than or is equal to integral of modulus of f of z, and this is z minus alpha, modulus of z minus alpha whole square, and this is modulus of dz. Here, now you see over here in this, if you look at this picture, this is on this curve C we are making all this integration. On this curve C we are making all these integrations. So the points Z must lie on this curve C. And what is this? This is actually a curve, and this kind of curve actually a bounded and closed sets. And if we have a function f of z which is analytic on any set, then it means it is differentiable or derivable. And if it is differentiable or derivable, in that case it is continuous. Okay, in that case it is a continuous function, and continuous function on this kind of bounded and closed set. And we know that a continuous function defined on a bounded and closed set is always a bounded function. That means f of z, modulus of f of z is less than certain number small m, less than certain finite number small m for all z belonging to this curve C. Okay, and therefore we can now further write this inequality as less than is equal to, let me write it over here, this inequality, this one on the left, so we can write it in this way. This is less than is equal to how much? This should be is equal to capital M. And on this curve C, you see on this curve modulus of z minus alpha is equal to this radius small r. Therefore in place of this modulus of z minus alpha we can put small r, and therefore this expression is we can m by r square can be taken outside the integral sign. Now this is our modulus integral of this modulus of dz, and that is nothing but is equal to the length of this curve, length of the curve C. Okay, so that is equal to length of the curve C means twice pi r, the perimeter of the circle. Okay, and then just cancel them out. this expression twice pi, these expressions, and then this twice pi will get cancelled, and this r and this r will get cancelled. So we have this kind of expression m by r. Got it? Now you see, if we now take what was r, this r was actually an arbitrary real number. This radius r was any arbitrary real number, finite of course. R is less than infinity, no problem, but now we can take the limit. Although r is less than infinity, but we can take the limit as r tending to infinity. R will always remain less than infinity, just we are taking the limit as r tends to infinity. And if r tends to infinity, in that case you can say that this quantity will tend to 0 as r tends to infinity, and this is permissible only because of the fact that r was taken to be as arbitrary real number. So what we have, we actually have that f dash alpha, modulus of f dash alpha is tending to 0 as r tends to infinity. Or you can say that this is possible only when this left hand side is equal to 0, because r was any arbitrary real number. That should be true for any real number r. So this is possible only when that this left hand side is equal to 0. So we have this expression, this f dash alpha is equal to 0, or in other words, this f dash, or simply this f dash alpha, one of modulus of f dash alpha is also is equal to 0. And modulus of f dash alpha is equal to 0 means this f of z, or f of z, this kind of f of z, alpha was taken to be any arbitrary point on the complex plane, on the finite complex plane. So this result should be true for all alpha, for all alpha, or you can also say that over here f dash z, just replace this alpha by z. F dash z should be is equal to 0 for all z in finite complex plane. And if it is so, it means that f of z must be a constant for all z in finite complex plane. It means that f of z is a constant quantity for all z in the finite complex plane. That was the statement of the theorem, that if a function, if you consider a bounded integral function, then such bounded integral function is always constant quantity. That this was the bounded function. It is bounded by from upper side by this m, and therefore we conclude that this kind of function f of z, this kind of functions are actually constant functions. Okay, so this concludes the proof of this theorem. I am going to start the last part for this lecture, that is the fundamental theorem of algebra. Fundamental theorem of algebra. Fundamental theorem. Actually, fundamental theorem of algebra, that is true for different in different context. We are proving this result because in algebra, this fundamental theorem of algebra is all about the polynomial. And a polynomial can be constructed by the help of a complex number as well. So over here we are going to prove this fundamental theorem of algebra. What does it say? It says that every polynomial equation of degree greater than or is equal to 1 have at least one root. Every polynomial equation of degree greater than 1, or let me write it in this way, greater than or is equal to 1. Greater than is equal to 1 has at least one root. Alright, every polynomial of degree greater than is equal to 1 has at least one root. Now, how to prove this result? Let's prove this result. We consider a polynomial function. Let us call it p of z, polynomial function. Maybe like this: a0 z to the power of n plus a1 into z to the power of n minus 1 plus a2 z to the power of say n minus 2, and so on, plus the last term would be is equal to say a n. Okay, and you see, this is, we are trying to define a polynomial of degree n, so this term should be not equal to 0, or in other words, this coefficient a0 should be not equal to 0, so that it remains a polynomial of degree n. So we are applying a restriction that this a0 is not equal to 0. So we are applying this kind of restriction. Now, what is the theorem? It says that this kind of polynomial must have at least one root. That means it says that this kind of equation must satisfy this kind of polynomial. If you consider this polynomial equation, this kind of equation must be satisfied for at least one one value of the variable z. Over here, z is a complex number. And you see these coefficients a0, a1, a0, this a1, a2. These are also complex numbers, not necessarily real numbers. So this we have to prove that this relation, if we consider this kind of polynomial, then at least one point is there which will satisfy this kind of equation, polynomial p of z is equal to 0. We shall have to show that there is at least one value of z which will satisfy this equation, p of z is equal to 0. Now we are considering some contradictory result, or we assume that if possible, we don't know whether it is possible or not. If possible, let us suppose that this p of z is not equal to 0 for any value of z in the finite complex plane, or you can say for any finite z. Okay, for any z in the finite complex plane. Okay. So for any finite z, we suppose that, if possible, we suppose that p of z is never equal to 0. Now, if p of z is not equal to 0, then what happens? Then what we can say? Then we can say that 1 by p of z, this expression, 1 by p of z, you see over here p of z is actually a polynomial function, so we can easily differentiate all these functions. So these are this kind of functions, you can say that these are actually analytic functions. And we suppose that this kind of analytic functions are not equal to 0. P of z is a polynomial, you can always differentiate them whatever times you consider, 1 times, 2 times, or whatever you consider. Anyway, so we can say that this p of z is a is always differentiable for all value of z. Therefore, it is an analytic function. And over here, this is our assumption that p of z is not equal to 0. And if it is so, then its inverse 1 by p of z must be an analytic function. It is an analytic function for infinite complex plane, of course. Okay, because we assume that this is true for finite z, for all finite z. So in finite complex plane, this function 1 by p of z is analytic throughout the finite complex plane or throughout the finite z plane. and this kind of functions are called integral functions. 1 by pz, which is analytic in the finite complex plane. This kind of functions are called integral functions. And also you see what we have over here, this kind of function 1 by p of z. How does it look? 1 by p of z. Just let me just copy and paste this expression. This expression like this. Okay, and you see this can be written as, you see, if it is in this expression, we just take z to the power of n common from this denominator. So if we take z to the power of n common, in that case this will come outside the bracket, and over here we have z to the power of n minus 1. So we shall have this kind of expression 1 by z, this kind of expression. Okay, in for the second term we shall have 1 by z square, this kind of expression. For the last term we shall have 1 by z to the power of n. Now you see over here, if we take the limit z tending to infinity, z is a finite complex number. Okay, fine. That means z is not equal to infinity, but we can take the limit as z tending to infinity. If we take the limit as z tending to infinity, then this kind of expressions 1 by z, 1 by z square, 1 by z to the power of n, all such expressions will go towards 0. So this expression will be is equal to, or it will tend to 0. Only one non-zero contribution would be there. So what would be the value of this expression when z tending to infinity? Its value would be is equal to a0. So this is a finite number. A0 is a finite complex number. Along with the fact that you see this can also be written in this fashion, 1 by z to the power of n. 1 by z to the power of n, like this. Okay, so this is a finite complex number. When z tending to infinity, this tends towards a0. This total expression will tend towards a0. So the value of the total expression is equal to 1 by a0. That is a finite quantity. However, along with this finite quantity, we have one more quantity multiplied over here. And if you take the limit as z tending to infinity, this value is equal to 0. So 0 multiplied by a finite complex number, that would be ultimately equal to 0. So we can say that this is tending to 0 as z tends to infinity. What does it mean? It means that 1 by p of z, 1 by p of z, it is it is tending towards 0 as z tending to infinity. So if we apply the epsilon delta definition, what we can say? We can say thus, for any epsilon greater than 0, there exists you can write a delta, or you can write a large number m, that m z tending to infinity. So let's write a large number capital M, of course greater than 0. Capital M, over there capital M is greater than 0, such that you see this quantity 1 by pz tending to 0. So this quantity, modulus of this quantity will be smaller than any small number, like less than epsilon, when this modulus of z is this z is tending to infinity. So modulus of z would be larger than any large number n. Or you can also write it in this fashion, that z is greater than m. You can also write it in this fashion, or z greater than m implies this inequality, 1 by pz less than epsilon. Okay, you can also write it in this fashion, that modulus of z greater than m implies 1 by pz less than epsilon. Now you see 1 by pz is less than epsilon, fine, no problem. Let us call it relation number 1. Let us call it relation number 1. Okay. Again, you see, we already discussed the fact that this 1 by pz is analytic in the finite complex plane. Therefore, if we consider the region over here, we consider the region modulus of z greater than m. Just try to understand this picture. Let me just draw this picture. Modulus of z greater than m. Sorry. So over here, this is the complex plane, and if you consider a circle of radius m, this is suppose m. So this is the zone that modulus of z greater than m. So in this zone over here, we have the result that 1 by modulus of, or simply you can write 1 by pz, if this modulus is less than epsilon in this zone. Okay, now our target is to satisfy similar result inside this circle. That means when modulus of z is less than certain quantity like m. And what is it? This is finite complex plane. This is finite complex plane. And we have this entire function 1 by p of z is an entire function. Got it? So within that finite complex plane, we have an analytic function within this kind of function, finite complex plane. So we actually have this kind of analytic function 1 by pz is analytic in this finite complex plane, and as because it is analytic within this finite complex plane, it must be continuous and bounded there. As because it is continuous within this kind of domain, therefore it must be bounded. So we can say this is a continuous function. And what is this kind of zone? You can also include the boundary modulus of z minus m less than or is equal to m. Why? Because if we include this boundary, in that case this interior portion given by modulus of z less than or is equal to capital M, because this becomes the complement of greater than m. Anyway, this kind of set modulus of z less than m, this interior along with the boundary becomes a closed set. Bounded and closed set, and within this kind of bounded and closed set, a continuous function is always a bounded function. We know on a bounded and closed set, a continuous function is always bounded function. So we can now say that 1 by pz is continuous, not necessarily the finite complex plane, or you can simply say in the region modulus of z less than or is equal to m. That is the mathematical expression over here. Okay, as because it is continuous within this kind of bounded and closed set, therefore this function itself 1 by p of z, this function itself would be a bounded function. Bounded means that there exists one number, maybe k greater than 0, such that this expression is bounded. That means such that modulus of this expression is less than or is equal to this quantity k for all z when z satisfy this region, or you can simply say in modulus of z less than or is equal to. So we have this second relation, say let us call it relation number 2. Okay, so what we have outside this region, outside this kind of region, we find that this relation is satisfied. This is our relation number 1. Inside this region, this relation 1 by p of z modulus of this kind expression is less than k is satisfied in modulus of z less than or is equal to m. This is the inside of this zone, and this is the outside in modulus of z greater than m. So if we now combine both regions, inside and outside, okay, inside and outside, we can say, can we say that 1 by p of z, 1 by p of z, this is less than or is equal to, or just consider the less than symbol, because over here we have less than inequality and less than inequality, that is less than is equal less than maximum of this k and epsilon for all value of z in the entire complex plane. Okay, over here we can say that if you see this is the maximum value, maybe this epsilon is equal to 0.1 and maybe this k is equal to 200. So we don't know which one is larger or which one is smaller, but in any case we can say that 1 by this pz, this quantity is less than the maximum, so that would be less than is equal less than 200 in this case, the maximum value. So if we now suppose that 1 by p of z is less than maximum in between k and epsilon, in that case we can say that yes, relation number 1 is also satisfied, relation number 2 is also satisfied. What I am trying to say is that 1 by p of z is a bounded function. So we have 1 by p of z is a bounded function. All right. So we can say that this expression is less than is equal to maximum in between epsilon and k. It means that 1 by p of z, or simply this expression 1 by p of z is bounded in finite complex plane. Now, if it is bounded in finite complex plane, then by Leopolis theorem, this quantity is a constant quantity. Suppose C. This quantity would be a constant quantity. And what does it mean? It means that P of Z, that would be is equal to 1 by C. P of Z would be is equal to 1 by C. You see, what is P of Z? P of Z is actually a polynomial, this kind of polynomial. And the value of the polynomial, should vary as we consider different values of Z. It can never be equal to a constant. It can never be is equal. It cannot always become is equal to the constant 1 by C. It should change as we take different values of z. As we take different values of the variable z, this expression should have different value. It can never always be equal to 1 by c. So we actually obtain a contradiction. Why did we obtain this kind of contradiction? Because of the fact that we assumed, if possible, we didn't know whether this is possible or not, but we assumed that f of z is not equal to 0. That was our assumption. And because of this assumption, we finally find that a polynomial expression always becomes is equal to constant. This is not possible. So our assumption was wrong. All right. And from that result, this assumption was wrong for all z, pz not equal to 0 for any finite z. This assumption was wrong. So what would be the correct conclusion? What would be the correct conclusion? If it is wrong, p of z not equal to 0 for any z, then we must say that p of z must be is equal to 0 for at least one value of z. Okay. So p of z must be is equal to 0 for at least one value of z. And let us call such value maybe say z0. P of z must be is equal to 0 for at least one value z0 of the variable z. Or in other words, we can say that z0 is the root of the equation P of Z is equal to 0. Got it? Z0, this is a polynomial equation, and Z0 becomes the root of the equation. That was the fundamental theorem of algebra. So this was the statement. It says that every polynomial equation like P of Z must have at least one root. Okay, so we conclude that P of Z must always have at least one root Z0. So this completes the proof of the fundamental theorem of algebra. And along with this proof, let me just show you a corollary. What kind of corollary you see over here? If you consider the if you consider any constant c, then this result says that this corollary says that f of z minus c will be is equal to 0, or you can simply say not necessarily f of z, like p of z. P of z minus c will be is equal to 0 for at least one value of z, for at least one value of z in the finite complex. Now, in order to prove this result, you see, if we consider f of z is equal to this p of z minus c, you see, if p is a polynomial function, then c, just subtract a constant, maybe complex constant, but p of z minus c, that would remain be a polynomial quantity. This kind of expression, just like this, minus c, nothing else, just the constant value will change. It will remain be a polynomial quantity, and again